Okay, so now I think it's good. Okay, so do you have my screen now? Because if just one of you just unmute and says something, because otherwise I have to go to the other browser.
I can see it. The screen is here.
Okay, great. Thanks. So let's say that so we talked about one-dimensional systems, and we also talked about its bifurcations. And this session, I don't think we actually can talk about bifurcations in 2D systems, but we go into 2D systems, and it's important. And if you just understand the 1D system, it's just just extending the ideas of the 1D system. That's all. So in 2D systems, we say that we want to find something like state of the system in the phase plane, and then doing the analysis on the phase plane. So in general, we have x dot equal to f as a function of x and y, as well as for y dot, g as a function of x and y. And this x dot and y dot, you can say that if x is the position in the x direction, then x dot is its velocity. So velocity means that it's a vector which has a scalar like an amount as well as a direction. So then we say that x dot and y dot is a vector field on the phase plane. So for illustrating this, we say that we have y and x, and we have a state like x and y, and these red arrows, they are x dot and y dot, which are vectors. And by combining all of these vectors, we can find the trajectory, which is shown by blue. Uh, it's again, it happened. Sorry for this. Okay. So, so if this state will follow this red vector, which is kind of tangent to this trajectory, and this trajectory is going to be created by all of these vectors. So that's all. So this state is governed by this vector. So solution again. Sorry for this. So solution xy gives the trajectory on the phase plane. The solutions, it means that the whole x dot and y dot. So as Professor Pipa said in the lectures, the 2D system, you can say that like x dot is equal to ax plus by. Is it linear or unlinear? So we call it linear because there is there all of them are just first order. We do not have, for instance, x squared. We do not have y squared. We do not have like x times y. We don't have a function like e to the power x or whatever. We just have x and y, and these a and b are constants. Therefore, x dot equal to ax plus by, as well as y dot equal to cx plus dy is a linear system. So we just say that if x and y is equal to 0, like here, you can put it like x, y, 0, 0, 0, therefore x and y, all of them will be 0. So the change in x depends on the chain, on the position on the x and as well as the y. But if all of them are zero, therefore x dot is zero, therefore there is no change, therefore it is a point which is fixed forever, therefore we call it fixed point. So x dot and y dot will be 0 and 0, therefore this fixed point always exists. It doesn't matter how much is the amount of A, B, C, and D's. That's all. So if we just want to show it in so you saw it in the lectures, right? So x dot like a vector, we show it like a vector. These are the vectors, and this A is a matrix, which is the representation of these coefficients A, B, C, and D. X, the vector of x is x and y, the vector of x dot is x dot and y dot, and we just say that x dot as a vector is equal to a matrix like A times a vector named x. So just interrupt me whenever you needed any concrete answer or something. So the solutions of this system, x dot equal to ax, can be visualized as the trajectories moving on the xy plane, which we call it phase portrait. Here I did a mistake, which we call it phase portrait or phase plane, in the phase plane. So this is an example. This is an example. It's the example of a simple harmonic oscillator. So suppose that you have a string here and you have a mass here, and this is the positive direction of x. And if I take this this mass and push it or pull it, doesn't matter. If I give a force to it, then you will see a kind of change here, which is an oscillation, right? So if the x is the position of it, then x dot is its velocity. So if we just checked, I want to bring this 126 page of Strogat's book. Yeah, so here you can see that that this oscillator actually it has a state like A, which the velocity is changing during this, as well as its position. So therefore we have a kind of velocity which is x dot as well as x. So we call it like our phase portrait. So in A it is like it's so if it is just in the origin, so it stays, right? In the origin there is no change. This is the point that we said like x star and y star equal to 0 and 0, and it doesn't have any interesting aspect, so we just always have it. But for different values of x, if you just push it or pull it, then you will see a kind of trajectory like this, which we are going to make it now ourselves. So if you follow those videos that we had, you can write it like, or here you can just see it, right? So if I just call that velocity like y, then x dot is equal to y, and y dot, so x dot is equal to y. So what is y dot? Y dot is x double dot. So this is y dot, and if I bring this to this part, then it's minus kx over m, which is this. right? So if we if we want to look at it like in our phase plane, you can now do it, and please do it. If now it is running in your system. So this is equal to y x prime, and y prime is equal to minus k over m, like in parentheses, times x, and we call it like k, which can be like 1, and m, like our mass, can be 2, for instance. And then by graphing the phase, you can find these null lines, and what these null lines has with these equations that we have here: x prime equal to y, therefore x prime, if y is equal to 0, then x prime is equal to 0. So if y is equal to 0, like this red line, then x prime is equal to 0. Therefore this is the null line of x prime. For showing the null lines, you can use here. So this null line is telling you also the direction in this phase plane as well. So if you remember in the lectures by Professor Pripa, these null lines are splitting your phase planes to some important and same in behavior regions. So you can see that these vectors that actually coming from the vector fields, which you can follow here. You can see this, and for finding the equilibrium point, you find the intersection of the null lines, and this is the equilibrium point, and these are coming from the Jacobian matrix here. For instance, here it's like 0, 1, minus 0.5 and 0, and you've seen this, how to calculate this, but again we will talk about it as well. And so if you just again double click on it, you will see circles, which tells you about the trajectory of the system, right? So these are those A, B, C, and D regions in your here. A, B, and C, and D, 4 different behaviors. One of them, the x is increasing, it is going to be more positive, and the velocity also is positive, and different types of them. X is positive, velocity is positive. X is negative, velocity is negative. X is positive, velocity is negative, and vice versa. So you have 4 different parts.
So is this an orbit or or a spiral, because the system is damping?
This is an orbit. This is not a spiral, but soon we will talk about we add a damping term, nonlinear damping term, to this equation, and then we will see the spiral. But here it is just an orbit. Yeah, a closed orbit. Good question. So yeah, so the origin, as you saw, is the fixed point, and the phase point would circulate around the origin and eventually returns to its starting point. This is why we call it closed orbit. And the phase portrait is all the trajectories in our phase space. These are just naming, just getting familiar with the terminologies. That's all. So now if you did it, we can go to the next part. You let me actually ask you whether all of you are running these p-plane and d-field. Okay, Hunay, probably you have a good imagination as well. That's the best. So,
No, I can't observe your work while I do it, so it's hard to move back and forth.
ah, okay,
So I will use the recording to try it later.
okay. So let's continue then. So if in another example, like example 2, if we have like x dot equal to ax again, where a has a variable like our matrix has a variable like a, which it is not a variable actually, it's a constant, but we just want to see different behaviors with different choice of a's. That's why we just put it as a. It is not a variable in the system. So we just say a like a constant. It can be 0, it can be 1, it can be -1. So we talk about it. So if again I have this x dot vector, and it is x dot and y dot equal to the matrix of a 0 0 -1, so it means that these two are 0, right? These two are 0. Therefore here these two b and c are 0. Therefore x dot does not depend on y, and y dot does not depend on x. So therefore we have x dot equal to ax, which just depends on x, and y dot just depends on y. It means that the change of x does not depend on y. Therefore they are not coupled, they are uncoupled. So we have these two equations, right? It's very simple. I'm sure that you can follow. So we have x dot equal to ax. What is x dot? It is d over dt of x, dx over dt. And on the other side we have ax. So if I bring this x to this part, then I have 1 over x dx, and if I bring this dt to the other side, I will have a dt, right? So after that I can take these antiderivatives, and the antiderivative of 1 over x dx is ln of x, and at, because a is, as I said, it's a constant, it does not depend on t, it is at plus just a constant which we always have in our integrals. So again they are equal, therefore I can have an exponential function to both sides. Therefore I have e to the power ln of x equal to e to the power at plus a constant, which a to the power a constant can be splitted like this and like a time, right? So if I have e to the power at plus a constant, it is equal to e to the power at times e to the power that constant. And and again this is a constant, so I put it like x naught as a constant, and I still have this e to the power at, and here this e and this exponential function and this logarithm function with the base of natural number. They are canceling each other out. Therefore, I have just x as a function of t. So x is equal to x naught e to the power at. You can also say this about y dot, right? So if you just think of it like a as -1, therefore it is exactly same, like dy over dt equal to minus y, and again I bring y to this side and I bring dt to that side, and I take the antiderivative ln of them, and then finally I have the function for the solution for y, which you see that they are pretty much similar, just a is -1 here. So if you also have dd field, right? So if we want to find the trajectory of x with, it is not a trajectory actually, it is not y with respect to x, it is x with respect to t, right? So if you again run the dd field, and so you have e to, what was that, x is equal to a constant times e to the power at. So a times t. And again I have, for instance, I have a as 1, therefore I will have this is x prime of t is equal to exponential of at, right? E to the power at. So if this a is positive, then I have just exponential growth. So x with respect to t, it is just an exponential growth, right? And you can see it here. However, if it is -1, then you see that it's pretty much going like asymptotically, just growing, however very very slow. And if it is just 0 again, you see that it's just 1, right? So this is the behavior of x with respect to t. And if we want to also talk about, by varying this a, talk about the phase plane, we can see it here, right? So x prime is what was that? This is I am wrong here. I should write these things. A times x. A times x, and this is minus y. And a is 1, for instance. And you see that again we have a kind of we have this saddle node, which these two null lines are, the intersection of them will be the equilibrium point. And it's very interesting that as time goes to infinity, positive infinity, then x of t is approaching x star, but it is absorbing to this null line and repelling from this null line. And you can also talk about the other ones as well, right? So if a is equal to 0, you see that you just have a null line that all of it is the fixed point, and all the state of the system will just absorb to this null line. And if a is negative, then you see that you will have a stable fixed point. All of the trajectories are just absorbing to this point. So that's it, and it's important to understand some important things here. It's a very good example. So if a is less than -1, if I put it like here, like for instance -2 or -10 for instance, then I have this system, right? X decays faster than y. What it means in the phase plane. Also, you can where is this? So this is the equilibrium point, and if I choose a trajectory right like this, then I see that x is so much changing so much faster than y. Y, just you see these grids, right? Y is changing much less than x, and everywhere it's same. X is changing much more faster than y. So this is when actually we have a less than -1. So I'm saying that by changing these parameters you can see different behaviors. And x star is the stable node, right? X star here is the stable node, and all of them will converge to this, and there is no repelling from that. If a is -1, as we saw, x star is a star, which just because of its shape we call it a star. It's not important, and it doesn't happen that much. And if a is between -1 and 0, what it means, what kind of behavior we can see? We can see a completely different shape here. All of them are absorbing to, you see that all of the trajectories are absorbing, and there's a kind of tangent here. All of the trajectories in these two regions, with all of the trajectories in these two regions, are kind of tangenting each other. And again, you can see the difference in the decay and the growth. And here, like in contrast with this one, here x decays faster, but here x decays slower, right? So if I have, for instance, here I have a very big change in y, but a very small change in x. So it's slower than y. X slower than is slower than y. So if a is equal to 0, as we saw, you just have a line of fixed points on x star, because e to the power, because this x dot is equal to 0, and then x of t is equal to x naught e to the power 0, which is 1. Therefore x of t is always equal to x naught, and all of this line is the fixed point. But the interesting thing is when a is positive. This is very interesting and very informative. So let's say, for instance, 10. So in this case, like a positive, we still have x star as our unstable fixed point, and by unstable fixed point we mean that if I just find the equilibrium point, which is unstable here, it means that these vectors are repelling from this, but but from here, this null Klein, actually this null Klein, it is, if I let me actually show null Kleins plus arrows. So these null Kleins are attracting toward equilibrium, but this null Klein is repelling from it, right? So this is actually the thing that is very important and governing this. Y-axis, we call this null Klein, like if I again change it to this arrows, we call it like just as a manifold, but stable ones and unstable ones. Stable ones are the y-axis, because it is just, it is just attracting to the equilibrium, and if I leave a state here, then it is coming back to this point. But if I leave a state here, then it is repelling from it, right? So we call it stable manifold and unstable manifold. However, this is the interesting thing. The trajectories, like this is the time. As time goes through infinity, the trajectories approaches the stable manifold. As time goes through infinity, or let's say minus infinity, it is absorbing to the unstable manifold. This is the unstable manifold, right? So as you see, it is absorbing to this null Klein, attracting to this null Kleins. As time, we are talking time here, like it seems that it is counterintuitive. However, this is the evolution of the system. So we say that all of these all of these states of the systems are going through this toward this stable manifold, unstable manifold, and you can just change the sign of time and say that the trajectories approaches to the unstable manifold. So it's not important actually, just the beauty of it. Okay, so I think yeah. Any question until here? No. Okay, so classification of linear systems. So we had this, and you also saw in the lectures. I also recorded the video, and you can also find that as well. But just as a recap, it's not really hard, but it is important. It's very, very simple. Very, very simple. You will see. So we have a system like x dot equal to ax, right? This is the position, this is the velocity. And A is those A, B, C, and D. So I also have a matrix like, this is just the notation. A matrix like identity matrix, like 1, 0, 0, and 1, and then if I times lambda times I, then the lambda and lambda will remain here. And for finding the eigenvalues, which Professor Pipa talked about, the determinant of this matrix should be equal to 0. The matrix like this A minus lambda I. It's just the approach of it. It's not important. At the end you will see that what is important. But for finding the determinant of this, you will see that this A, B, C, and D, which is coming from A, and this minus lambda 1 and minus lambda 1, again here, it is coming from this minus lambda times the identity matrix. And the determinant of a matrix like this, which is 2 times 2, is multiplying the elements on the diagonal of the matrix minus the multiplication of the elements of on the off diagonal of the matrix. So it's going to be A minus lambda times D minus lambda minus BC should be equal to 0. And therefore I just say that A times D, A times minus lambda times D minus lambda times minus lambda, which is lambda squared, minus BC is equal to 0. And then I factorize these lambdas, and it's A plus D, and I bring this AD to here, and this is AD minus BC. Therefore I have a formulation like this, like lambda 2 minus A plus D times lambda plus AD minus BC is equal to 0. We call it D, like the depth, and we call it tau, like the trace of our matrix. It's just the name. It's all coming from here. A plus D and AD minus BC. This is the important thing. So, is there any question here? The eigenvalues, I can just tell you like this. If we have a linear system, and if the eigenvalues, eigenvalue, right? This is not a vector. This is a value. This is like a scalar. Lambda. Lambda is kind of scalar. It's a number. So it means that your system, like the coordination of your system, is enlarging or getting smaller. If it is, for instance, if it is lambda is equal to 2, then the system, your system is the amount of coordination of your system is getting bigger twice. That's all. But the lambda is the eigenvalue, and in this here, for instance, you have a vector like x, right? So if you find the lambdas for like corresponding to those lambdas, the eigenvalues, you can find the eigenvectors as well. But we don't work with that. I mean, we actually work exactly with that. These are the vector fields, but we are not going to compute them now, right? But yeah, this is the basic thing. So now next example. Is there any question until here? No. So next example is I am trying to talk about linear formulations, right? So x dot is equal to x plus y dot is equal to 4x minus 2y, and then I have this a, which is 1, I have this b, which is 1, I have this c, which is 4, and I have this d, which is minus 2. Therefore the trace of my matrix is a plus d, which is equal to minus 1, and the depth, which is AD minus BC, is equal to minus 6, right? Which is BC, like this 1 times 4 is minus 4, right? So minus 2 minus 4 is equal to minus 6. And then my formulation will be like this: lambda 2 plus tau minus tau, which is itself is minus 1, therefore it is plus lambda plus det, which is the delta, which is minus 6, is equal to 0. And if I want to find the roots of this equation, it's like lambda minus 2 times lambda plus 3. So you can see that here, for instance, lambda times lambda is lambda 2, which is this. Lambda times 3, I have a 3 lambda, and as well as minus 2 lambda, therefore two of them cancel each other out and one of them will remain. And minus 2 times 3 is minus 6. Therefore this is equal to this. You can see, and so if it is going to be equal to 0, therefore one of them at least should be equal to 0. Sorry. Therefore lambda 1 is equal to 2, like here. If I put the lambda equal to 2, it's going to be 0, or this one is equal to be 0. So these are the roots. So this is lambda 1, lambda 2. These are my eigenvalues, and therefore for the positive values of our eigenvalues, we have growth, and for the negative values we have decay. We have growth and decay, which is coming from those e to the power lambda t. And because one of them is positive and the other one is negative, then we have a saddle node in our origin, which like these classifications, I also pre-recorded some videos and you can find it, and in the textbooks as well. But now let's use the p-plane and see the trajectories. These are the equations, like x dot equal to x plus y. Y dot equal to 4x minus 2y. So again, I have these null lines, and maybe I can find it here as well. And these lines here, as you saw, I chose plot stable and unstable orbits. So here there is no orbit, it's a line, but these are those lines that we were talking about. These are the ways that actually you see that the vector fields exactly are governing, and these are actually splitting your phase plane to 4 different regions, and you can find where it crosses the null lines and what will happen for your system. So find the equilibrium point. Again, here this is the equilibrium point, and if I want to see this trajectory, you see that this trajectory, it is crossing the null line, but these stable and unstable orbits that we talked about, these are the intersection, and also you can find in the lectures by Professor Pipa, and these are the regions that actually change. You have 4 different regions here, right? So this is if I want to show the null lines with arrows. So these are the arrows, and you can again see that it's repelling from the origin, which is a definition of saddle node. Therefore it is saddle. So okay, so if the eigenvalues are complex, it means that under the solution, where is the equation? I can't find it. The solution which is coming from those you have a second order equation, like lambda 2 plus a constant times lambda plus another constant equal to 0. Then you can find that actually if the under square root of it, which is tau square minus 4, that if it is negative, it means that under the square it's going to be imaginary, and therefore we have complex numbers. And then our eigenvalues, which are lambda 1 and lambda 2, will be alpha plus minus I omega. These are, you can say, A plus minus IB, right? But because this imaginary number is intuitively, it is a representation of rotation, we call it omega here. And this alpha is talking about the rate of, like, the amplitude, the real part. Therefore we call it alpha. So this alpha is equal to tau over 2. You can follow the equations here in my previous videos. Also Professor Pipa talked about this as well. But I have 3 different ways. If alpha is positive, then my oscillation is growing. And what does growing mean? It means that my fixed point is unstable because it is going away from it. And if it is negative, then it is going toward it is. Therefore it is stable, and I have a decaying oscillator. And if this alpha is equal to 0, it means that tau is equal to 0. It means that the trace of my matrix is equal to 0. It means that A is equal to minus D, as you saw in the BD toolbox, and we go and talk about it if you want. And this is going to tell you that this is pure imaginary, and this is a center. This is so I forgot to write it here actually. These two are spirals, and this is the center. So we have spirals and centers. So figure in 137. So just so this is the center, and this is the spiral. This is the spiral that's like an stable one, and the unstable one is spiraling out. Keep going, huh? And yeah, so 135. So just tell me if there's a need. Any of you remember the linear OD in MATLAB? Should I do it again, you think, or you remember that those spirals and centers? Do you like to do that now, like in a very fast way? Yeah? Okay, let's do that. So I have its name is linear ODE. So we say that our system again is our linear ODE system, and here, just for the visualizing it, therefore my system will be like this, and so I have this A, B, C, and D, and these are my equations: x dot A, B, C, and D. And I am talking about imaginary numbers, which actually these A and D are exactly opposite of each other or not. It means that the trace of your matrix is equal to 0 or not. It means that alpha is equal to 0 or not. So if I want to see so here you can see the oscillation, which x with respect to t, you will see the oscillation which is coming from that uh, from that essence of imaginary number, and in phase portrait you will see a center. So this is what we call center. This is y with respect to x, and these are the null plines of it. You can just put x dot and y dot equal to 0 and find them. And these are the vector fields, and you see that the vector fields, all of them are like, if the state of system is here, it is just oscillating and oscillating and oscillating and oscillating. Why? Because the trace of your matrix is equal to 0. It means that A is equal to minus D. And if I just change it to, for instance, 1, then it's not valid anymore, and you will see spiral. And in your time portrait, you also see a kind of damping and converging through a fixed point if your spiral is stable, and if it is unstable, it is a spiral. It is spiraling out. So this is the choice of A and D, which is which we talked about it here. If this alpha, which is the trace of half of the trace of your matrix, if A and D are opposite of each other, alpha is 0, therefore you have a center. And if alpha is positive, then you have a growing oscillation, which you have a we had the alpha was decaying, right? Let's find this unstable fixed point, and so the alpha should be positive, therefore the trace of your matrix like A plus D should be positive. Therefore I just put it like 3, and then it's going to be positive, and you will see that it's big. You will see that it is spiraling out. Like, this is the initial condition, and from the initial condition it is coming out, not going toward. So so if we want to talk about here this you had a very better but similar figure in the lecture by Professor Pipa, that were actually splitting your imaginary phase plane here based on tau and delta, which by these choices of deltas and trace, so if tau is 0, then it is on this line, which means that this is the center, those oscillations. And if it is less than this, like under this curve of tau 2 minus 4 del det equal to 0, then you have unstable spirals, but still have the imaginary parts, because this tau 2 minus this amount is something negative, and it is under squared, therefore it is therefore you have oscillation, therefore you have whether spiral or center. So if it is in this region, it is unstable for positive traces of your matrix, and if it is in this region, you have stable spirals, which means that it is the trace of your matrix is negative, and it is attracting toward the origin or fixed point. And so out of this curve you will have unstable nodes or stable nodes, which just coming from the decays or growth. why here? Any question?
Yeah, I have this error. I can't troubleshoot it. I'm trying to run linear ODE on my computer and it says it is not found, even though I have added the path
Ah,
to
maybe you didn't
VHLKIP.
add the path. Have
I
you?
have added path.
Uh-huh. As well as its models, both of them.
Oh no. Oh, okay.
You mean? I
So
mean,
I have to add the models. I
yes.
didn't do that.
You should do both of them. Like, for instance,
Okay,
add.
yeah, it's working now.
Yes. Okay. Good.
So how is DD field run, which you were working on just now?
Sorry.
DD field.
Ah, DD field.
How do
Do you have Mac or you have
I,
another?
Linux Ubuntu 20.
Uh-huh. I think the command is like jar. So you have this. This is going to, and also you have Java, right?
Yes.
So you can run it actually. Here keep playing. Mm, the file, the command is. Why this here? No, this is not the one. This is the one. This is the command actually. Oh, yeah. Ah, where am I?
And this command has to be run on in MATLAB or is this for
No,
the
no, no. In
terminal?
your terminal, go to that path and just run it in your terminal, not on MATLAB.
Oh, I see. Okay, thanks.
Yeah, worked. Good. You're welcome. So we are almost going to finish, but soon. So we until now we talked about linear systems, and by linearity we meant that all of those x and y's they are just first order. But we can extrapolate it to nonlinear system, and you just say that take a function like f as a function of x and y for your x dot, and same for your y dot. And there is no hope of finding trajectories analytically. Therefore, definitely you need to computationally use these phase planes and understand your system. So we said here, for instance, I'm going to talk about Jacobian. That you also got the lecture, but for just for understanding and breaking these big names like Jacobians, like I don't know, like these eigenvalues, eigenvectors, and it's kind of unfamiliar and like a monster and these things. It's not like this actually. It's very simple. You can say that you have this x dot. This is a, right? So if I take the derivative of this x dot with respect to x, the thing that is remained is this a. If I take the derivative of x dot with respect to y, then this is the remaining thing is b. So this a, b, c, and d is actually coming from this taking these derivatives. So if it is, for instance, a times x squared, then the first derivative of x dot with respect to x will be 2 times a times x. The power of it is coming to be 1, like 2 minus 1 is going to be 1. So this is the same. This is exactly the same, and we just call it Jacobian. So this x dot will we have these functions, right? X dot is governed by f, y dot is equal to g. So we say round like this. This is the derivative, kind of partial derivative. It means that you should forget about y part. That's all. That is actually not all, because maybe you're some maybe it can be more complex, but we don't care about that. That's all. So we say that the first derivative of our f, which is x dot, with respect to x, which was a, right? But it can be bigger. If it is a x squared, then it's 2a x times x. And here, for instance, so you have four parts, and you have two variables f, and you have four variables f, x, g, and y, and you are taking the derivative for two of them. You just have two variables, x and y, but you have two functions, f and g. In general, as a combination, you have f, g, y, and x. Therefore, the first one, the first row, it is f. The second row, it is g, which is this, right? This is x dot, which is f. Therefore, it is f. This is y dot. Therefore, it is g. Therefore, it is g. And this first column is the first derivative with respect to x, the first derivative with respect to y. This is that A matrix that we were talking about, and times xy. That's all. So I had this in the linear form, right? So I just want to change it to nonlinear. For instance, I say ax times x cubed plus something else. Like here, for instance, we have an example. X dot is equal to ax, this ax, times another thing like x squared plus y squared, and so on. And you can also have this y dot as well. So I just wrote it like this because I can say actually ax cubed plus axy squared minus y, because if you just look at it like in a plane, like look at it like x2 plus y2 is equal to r2, I just wrote it like this. It's not important. And if you now we want to find the Jacobian. The Jacobian is the first derivative of the first equation with respect to x for the first element. This is ax cubed. Therefore, it is going to be 3 times ax squared. What is the first derivative of x dot with respect to y? It is minus 1. How about the first derivative of y dot with respect to x? It is 1. Round g over round x, which is this. Is this 1. And as well as this one. And it's going to be like in these fixed points, you have x and y equal to 0. Therefore, you have 0, minus 1, 1, 0, and that's your Jacobian. And for finding the eigenvalues, you just put the minus lambda, and then, or with the help of the trace and the data of your matrix. So we want to see about this equation actually, different values of a, and see these behaviors. So again, please use your p-plane as for the visualization, and this is the equation. why? So ax okay. Hmm. So I just wanna say that here, for instance, for the sake of simplicity, you can also write all, but just imagine it like ax minus y. It's basically it's same, uh, but we can write it as well. So I just say a times x squared plus y squared plus or minus y, right? And also we had a. This is the a, right? And for here, for y dot, x plus ay, x plus a times y times again x2 plus y. So this is my null lines again, and for this equation you see that the null lines are like this, and it is going away from it. Why? Because my a is positive. My a is 10 here and it is positive, and therefore it is going away from it. And if I again change it to show null lines and see the vectors here, you will see it's very big. uh, Maybe I don't know whether it's really, if I change it like this, I think it depends on this value, because yes, it's better now. You will see that again you have these null lines, and this is going to actually show your spirals. And it's a beautiful picture, right? It's really beautiful that all of them are coming from these mathematical things. So if a is positive, then your spiral is unstable. So you have this third one, like here. You can follow these vector fields for like your arrows. So if you just again change it to -1, then you again have the spiral, but it is going to attract. And maybe I can also plot the stable and unstable fixed points. If no, why? It is not a saddle point. Yes. It's really, you see, we can always learn. It is not a saddle point, right? Why it is not a saddle point? Because here, as you can see, all of them are repelling. None of them is attracting, and then again, or both of them are attracting. None of them are repelling. So if a is equal to 0, then those interesting things is coming out, which is this. And you will see that soon you can actually see those circles. So this is just important. Like if it is the solution of x of t, then this is just a constant like c times that solution, another constant, another bigger constant times that solution. So all of them are like same in behavior, but just the amount of them are different. And it's interesting that with some values of a and some constant like this, you will see uh, different behaviors. So let's take a look at practice sheets. In practice sheets, now it is very easy for you. So in practice sheet number 3, which I am very thankful of Devrim Klik for all of his efforts. So you can find the very organized practice sheets by his works, and so I talked about these null planes and phase planes, and the number of the fixed points and the null planes, and understanding the behavior of the system, whether it is growing, whether it is absorbing, whether it is a spiral, whether it's not, and stuff. So this linearization of two-dimensional systems, now we talked about that we used actually this Jacobian matrix. So if we have a system 1 like this, is it linear or non-linear? It is non-linear. Why? Because we have x2, right? X squared. Or we have x times y. So we have some functions, and this is a nonlinear equation. And again, for finding the null lines, you can put the x dot equal to 0. Therefore, one of them is equal to 0, right? So whether x is equal to 0 or 2 minus x minus y is equal to 0. And also you can find about y, this is y dot, and also you can find about y dot as well. The x null lines and the y null lines are achievable like this. And for the Jacobians, so this is the first derivative of f. What is f? F is here, like x dot is equal to this, right? So this is your f, right? Therefore, the first derivative with respect to x is this, right? 2 minus 2x minus y, right? Which is this. You just take the first derivative and with respect to x. And if you take the first derivative with respect to y, the only term that is remained is minus x, right? Here, x dot is equal to x times minus y. So if I take the first derivative of x dot, or f, with respect to x, therefore just the remaining part is just this minus y, right? So this is going to be minus x. And same as for your y dot. For your y dot with respect to x and with respect to y, you take the derivative of it, and this is going to be your Jacobian matrix. And for your fixed points, you found the fixed points, right? X dot is equal to 0 and y dot equal to 0. You can find the fixed points. And for instance, if x and y is equal to 0 here, x is equal to 0 and y is equal to 0, therefore x dot and y dot is equal to 0. Therefore, your Jacobian matrix in your fixed point, because we are using this Jacobian matrix for linearizing our system, like in neighborhood, in nearness, in the proximity of our fixed point for having an approximation. That's it. So the Jacobian matrix here, you can put like 0 and 0, therefore it is going to be 2. This is going to be 0, therefore it is going to be minus 1, and the rest is 0 and 0. So this is your Jacobian in your fixed point. So now we want to find the eigenvalues that we talked about. So this is 2 times minus 2 minus lambda times minus 1 minus lambda times 0 is equal to 0. Minus 0 is equal to 0. So if you have a diagonal matrix like this, in general these two itself are your eigenvalues. Otherwise you know how to systematically find your eigenvalues, right? Therefore one of them is positive, the other one is negative. Therefore we call it saddle node. Our matrix, our fixed point, which we found it with the help of this Jacobian matrix and finding the eigenvalues, we found that it is saddle node. And you can also have other fixed points as well, right? So if I take x here like 2, then it's going to be 0 again. Therefore with this choice of 2 and 0. So again I have this Jacobian for this new fixed point, which is this. I just put 2 and 0 here, 0 and 2 here, 2 and 0 here, and I calculate this, and it's this. And again I have, because I have this 0, so I forget about this, and one of them is minus 2. One of the eigenvalues are minus 2, one of the eigenvalues are 1. Therefore again they are opposite of each other, or you can systematically check this delta, which is minus. Therefore again I have saddle node. And as well as for the other fixed point, again you can find it. So this is 0, therefore I just have minus bc. Therefore I have minus 1 times 1. Therefore tau 2 minus 4d is equal to like a negative 1. Therefore I have the complex roots, right? This means that because the trace is negative, therefore we saw it like in our spiral, right? Therefore it is stable focus. So system 2 again is another differential equation. It's exactly the same. We just say that x dot is equal to 0 and find the fixed points and the null lines and the Jacobian, taking the derivative of them, like taking for instance this one, take the derivative like this g is y dot with respect to y. We should calculate this. If we find it here like y dot with respect to y, we just have this y2 minus xy, right? So therefore we have 2y minus y minus x. Therefore we have 2y minus x, and we calculate all of them. And again for those fixed points we just put the numbers here, and based on the sign of delta as well as our trace, we can find the stable and unstable nodes or the saddle nodes. And same for this system. So it's all of them are same. They are just, we can have a lot of them. And so this is this practice sheet, and I just have. Do you have any question here? Where is that? No. So it's going to be finished very soon. So my limit cycle is like we talked about those closed trajectories, right? Like those periodic orbits, closed orbits, like the center. So an isolated closed orbit is called limit cycle. It means that it is not actually always uh, cycle, but it's like these blue things. So we have basically we have three different of uh, limit cycles. One of them is a stable. It means that if a state of a system is starting from here, you actually have I it was my mistake actually. I should put a unstable fixed point here because topologically they should complete each other. Therefore, a state of a system here spiraling out and absorb and attract to this stable limit cycle. And however, out of this limit cycle, it is absorbing to this. Therefore, we call it stable one because every state inside and outside will absorb to this limit cycle. And this limit cycle is just repeating somebody has a question? Probably.
Uh, yeah, I have a question. Didn't want to interrupt though. Sorry about that.
Yeah.
So we know that the planet Mercury is in an orbit around the sun, and
Right.
despite that, we know that the movement of Mercury, the oscillation, has a certain perturbation. So, based on the knowledge from these equations, the orbit is fairly stable, but we also know that there is perturbation in the movement. So, I don't understand how these two pieces of information would align together because here we have evidence that an orbit is perfectly stable, but there we have a separate differential equation for how that orbit within itself is quite unstable and has an error margin.
Uh, this is kind of far from neuroscience actually, but thanks. It's an interesting thing. So um, it's coming from physics, right? So in physics, you should have velocity, and that velocity is center absorbing or center attracting, or center repelling, and based on the motion and the angular momentum actually, based on angular momentum you can write the proper equation for that motion. Actually, you are right. Even it's exactly even it relates to neuroscience because for instance for polar coordination we use instead of this x and y and the combination by combining them like x squared plus y squared equal to r squared, we define radius and angle, right? And by that radius and angle we can actually have a very informative representation of state. So yeah, I think your question should be answered better in maybe in two sessions later, which we talk about. I mean, I try to talk about those phi or theta, which representing the phase of your oscillation, and yeah, that's it. The time is over. I I should talk about it later, I think. Yeah. Or if you want, if you stay, I talk about it. I mean, I am okay. But I think you are tired as well. So we can talk about it later. So thank you for being here, and Was it good enough this session? I mean, wasn't it better than the other sessions? Great, thanks. I'm so much glad to hear that. Thanks. Thank you for having this much motivation. Okay, have a great weekend and hope to see you again next week. Bye.